Hello, welcome back to MEC 416/816 Engineering Acoustics. In this lecture, we are going to start talking about the one-dimensional elastic waves. That's chapter 2 for us. It's also chapter 2 in the book. We're going to start by deriving the equation for the transverse oscillations of a string. And we're going to consider this following string that I've drawn here. So in this picture, our horizontal coordinate is x, our vertical coordinate is y. The string has a total length of L, and the dashed black line represents the equilibrium position where there is no displacement, and the bendy gray line represents the string under some kind of deformation, some vertical displacement. So we can measure the vertical displacement using v of x comma t, and now it becomes a function of both time and space being x. The string is going to have an internal tension, T of x, and a mass per unit length, M of x. And then lastly, we are going to now apply or consider an external force per unit length of F of x comma t. Now, this F can act across the entire string, and I've only drawn it for a small part. But you should know that it can apply across the entire string to a part of a string at a very specific location, or it could be in multiple locations with breaks in between those locations. Okay, so like I said, v of x comma t is the vertical displacement of the string. All oscillations are going to be transverse and in plane, transverse being our vertical direction. F of x comma t is an applied vertical force distribution per unit length. We're going to assume small displacements and angles. And we have that internal tension T. We're also applying the continuum assumption. That means that there is, for all values from 0 to L, the string exists, meaning that we're not considering there to be atoms or anything. There is just always string, and you can zoom in infinitely, and you'll always find the string there. And then since it's a string, it cannot support any bending moments. What we're now going to do is we're going to zoom in on an infinitesimal element of that string, and then we're going to do a force balance. Right now we're going to draw a free body diagram, and then we're going to do a force balance on this. Okay, so at the position x, let me try redrawing that. At the position x here, the displacement is v of x comma t. At the other end of the string, we have a displacement of v of x comma dx comma t. I'm sorry, that should actually be v of x plus dx comma t. On the right hand side, we're going to have some tension here, which will be t of x pulling on the string. Then on the other side, we'll have a tension t of x plus dx. And the tensions each act at some angle. On the left hand side, we'll have theta of x comma t, and on the right hand side, we'll have theta of x plus dx comma t. And then lastly, let's add our external force distribution. Which again is f of x comma t. Now I mentioned that we have small angles, so at this time let's go ahead and add that in here. So when you have small angles, this implies that the sine of theta is approximately equal to theta, and the cosine of theta is approximately equal to 1, meaning that we can use theta and 1 instead of sine and cosine of theta respectively. And then small displacements tells us that theta is going to be approximately equal to the first partial derivative of v with respect to x. So that is the slope given by that displacement. Okay, at this point we're going to do a force balance across the string, and apply Newton's second law. We're going to start with the acceleration, and we're just going to consider the mass across the entire string itself. So we have m of x dx times the second partial derivative of v with respect to t. That's our acceleration. That's on our left side. That is the mass times acceleration term. Move this down a little bit. Then for forces, we are going to have first, we're going to have t of x plus dx comma t, and this would be multiplied by, since we're balancing the vertical direction, this would be multiplied by the sine of theta. However, we can use small angles here and instead just write theta of x plus dx comma t, then minus t of x times theta of x comma t. That is the vertical force on the left. And then lastly, we have our external force, which will be f of x comma t times dx. From here, what we want to do and are going to do is that we are going to expand the first two terms on the right-hand side, the ones that I'm underlining here. We are going to expand each of those into using a Taylor series approximation. We're going to expand using a Taylor series, and then we're going to truncate that approximation. So what this then gives us is that t of x plus dx, no t in that one, this is then equal to t of x plus partial t over partial x times dx plus higher order terms that depend on dx squared or above. And for theta, we will have theta of x plus dx comma t. This will be equal to in fact, we're going to invoke that small displacement argument. So we're going to first have partial v over partial x plus partial squared v over partial x squared dx plus terms with dx squared or above. So the O of big O of dx squared means the following. This will include terms like, actually we'll do it for the tension. So this will include terms like 1/2 partial squared t over partial x squared times dx squared minus 1/6 partial cubed t over partial x cubed dx cubed plus dot dot dot. So you can see that the leading order term inside that is contained within that big O has a dx squared in it. And then the next term has a dx cubed in it, and then there will be a dx fourth, dx fifth, and so forth. And we're just lumping all of those terms into this big O notation. And then ultimately we're going to truncate and remove that. And the argument is that dx is small. It's an infinitesimal length. So if dx is small, then dx squared is going to be extremely small, practically zero. And dx cubed is going to be practically zero, and same for all of the other dx powers. If you take a really small number and you square it, you get an even smaller number. You get a significantly smaller number. So what we'll then do is bring these into our equation of motion, and we'll get that, let me just switch back to red, we'll get m of x times dx times partial squared v over partial t squared is equal to t of x times partial squared v over partial x squared plus, times dx plus partial t over partial x times partial v over partial x times dx plus big O dx squared, lastly plus the force f of x comma t times dx. And at this point, we can just say that those are all equal to 0 and just truncate and get rid of those. And then you'll then see that we now have a dx in every part of the equation that we can eliminate. And actually, before we do that, is this equation as shown here, is this a linear equation or is it a nonlinear equation with the big O set to 0? And in fact, for mini homework, we'll say like 5 points. Is this equation nonlinear or linear? Okay, and let's have this mini homework be due in class You can just put it on a piece of paper, look into this and see if you can find out if it's linear or nonlinear, and what makes an equation linear, what makes an equation nonlinear. And then bring your answer into class on a piece of paper on, let's say, February 6th, and of course 2024. Okay. So then, as I was saying, we can now actually cancel out all of these dx terms. And then we're left with the following: m of x times partial squared v over partial t squared is equal to t of x. In fact, actually, we can pull out a partial derivative. So partial over partial x times the quantity t of x times partial v over partial x, closing that quantity, plus the external force f of x comma t. And this is what we consider the general wave equation. With mass and tension that depend on space. If we assume then that m of x is a constant m and t of x, the tension, is a constant big T, and there's no external forcing, then we arrive at the following. We can write that partial squared v over partial t squared is equal to c squared times partial squared v over partial x squared, where c here is equal to the square root of t over m, valid for 0 less than or equal to x, less than or equal to L, for t greater than or equal to 0. And again, that's our classical wave equation. So what is C? I would like you to pause the video for a minute or so and just take a moment and try and think about what C is. Try and come up with like a physical explanation for what you think C is. And it doesn't have to be the correct answer. Just try thinking of what it could be in general. Pause the video and think about it. Okay, welcome back. So I asked you to think about what C is, and C in this case is actually just the speed of sound. So it is the speed at which a wave will propagate, an acoustic wave, or in this case an elastic wave, will propagate down the string in either direction. Okay, so equation 5 is a second order partial differential equation that's has derivatives in both x and t, and its solution requires both boundary conditions and initial conditions. You have to have both boundary conditions, which tells you what's going on at the boundaries of the problem. That would be at x equals 0, x equals L. And initial conditions, at what happens at time t equals 0. Having both of these makes the problem well posed. If you haven't seen boundary conditions before, they are, in a sense, the same as initial conditions, except that they are defined in space, so at the two ends of the string. Whereas initial conditions are defined for the displacement and velocity for the entire string, the boundary conditions are defined for only the two ends of the string. All right, so for initial conditions, we're not going to do a lot with initial conditions, but if you had some function for the initial conditions, you could then incorporate them into your solution. But we're just going to use generic initial conditions in this class. So we'll say v of x comma 0, so again at t equals 0. This is going to be equal to, let's just say u1 of x. That's just some function of x. In fact, let's use a little bit more generic. Let's use h of x, and that is our initial displacement. And you can see it's defined for all x. Then v, in fact, partial v over partial t evaluated at t equals 0. And I'm going to introduce a new notation here. We're going to use the subscript t to define a derivative with respect to time, and then we'll use later on a subscript x for a derivative with respect to space. And then we'll say that this is equal to g of x. So that's our initial conditions, just two generic functions that depend on space. And let's just add a note here that subscript implies derivative. We're going to use this subscript to represent the derivative primarily throughout this class, and it just ends up helping us save time so we can avoid having to write all of these partial derivatives or partial symbols. Okay, let's talk about boundary conditions now. So like I said, we need two boundary conditions, one for each end, and there are different types of boundary conditions that we can study. We're going to talk right now just about the two simplest ones, which are a fixed and free end. And then in worksheet 1, you will go through and derive the boundary conditions for when there is a mass at one of the ends, like a discrete mass, and the boundary condition for when there is a discrete spring added to one of the ends. Okay, so for a fixed end, if we assume that the length of the string is preserved to first order after deformation, which is a valid assumption given the assumption of small displacements and small angles, then a fixed end will have no displacement at the end. And that means that we can write here that v of 0 comma t is equal to 0. That would be if it was at x equals 0. If it was at x equals L, then v of L of t is equal to 0. And that is the boundary condition for a fixed end at either x equals 0 or x equals L. Now, when we have a free end, which is the next simple boundary condition, we're assuming that there's no force applied to the free end, and that this little, I drew like a little ball here that's sliding up and down. There's no friction there, there's no mass associated with that. It's no force is acting at that free end. And in this case, we can write that, as shown here, we can write that t of x, in fact, we'll write it like this, t of x times v sub x of x comma t, this evaluated at x equals L, must be equal to 0. So it's not just that, it's not just the derivative v of x here equals 0, we also have the tension here. It's this entire term evaluated there. Now, if the tension t of L is not equal to 0, then we can write that Vx of L comma t must be equal to 0. So the first derivative with respect to x must be equal to 0 here. And then if we're considering at x equals 0, then we would write v sub x of 0 comma t, that is equal to 0. Okay, this concludes our lecture for the derivation of the wave equation for a string. In the next section, we're going to go through the derivation of the wave equation for an axial vibration of a bar.